So thank you for the invitation and for the introduction. So yes, I will talk about regular singularities of Mahler systems and an explicit characterization of such singularities, which is a joint work with Colin Faverjon. Before talking about Mahler system, I will talk about regular singularities of a more classical context, which is the one of differential system. So let's begin with the differential case. I will denote them by RS during this talk. Okay. So just before, I need to define what is a singularity of a differential system. And we say, by definition, that a point is a singularity of this differential system. Let's assume that A is a matrix whose entries are rational functions. Okay. If it is a pole of the matrix of the system. And we have the same definition for the point infinity. You just make a change of variables like this, and now you're looking at this system. And you look at the point, the singularity is 0. Okay, so you have the same definition. So that's for singularity. I will talk about the point 0, the singularity 0, but you will have the same kind of definition and result for other points. But just to fix ideas, let's look at the point at this point, okay, for what follows. I just introduce this change of derivation called delta, and I will call A this differential system of matrix A. Okay. So now I've defined what is a singularity. Before defining when it is regular, I need a last definition, which is the definitions of two equivalent differential systems. And we say that two differential systems are equivalent if there exists a matrix T whose entries are in the fraction field of the series convergent in a neighborhood of 0. Okay? This matrix is often called the gauge transformation. And so there exists such a matrix T such that you have that the matrix B is this one. You can express the matrix B thanks to the matrix T and the matrix A. Okay, it's that. And in fact, this definition is natural because you can check that if Y is a solution of the system of matrix A, then in fact this matrix is a solution of the system of matrix B. So you can express solution of B thanks to solution of A and this gauge transformation. Okay, that's why this definition is natural. And now I have everything I need to define what is a a regular singular system, differential system at 0. So we say that this differential system is regular singular at 0 if there exists a constant matrix C which is equivalent, which gives an equivalent system. Okay, so by definition, the definition of regular singular differential system at 0. And you have the same kind of definition at other points. Okay. So in this talk, I will mainly be interested in system, but of course you have the same kind of definition for equation. So just I mentioned here that we say that differential equation like this, okay, with L is this, okay. I took my AI in COZ. Okay. We say that this differential equation is regular singular at 0 if it's the associated differential system is regular singular at 0. If associated differential system is regular singular at 0, where AL is the companion matrix associated with L. Okay, so it's like this. Okay. It is because, as we saw this morning with Rémi Jaoui, we can transform a differential equation into a differential system like this. So I can, okay. Sorry. It's because if you have that y is a solution of your differential equation, then you can check that you have this equality with y is a vector. Here, my vector will be this one. Okay. So I will just mention some consequences of this property of regular singularity. Just before giving these consequences, I would like just to mention that for differential equation, we have a beautiful criterion to know when such a differential equation is regular singular at 0. It's called the Fuchs criterion. Fuchs criterion. And thanks to the criterion, we know that this differential equation is regular singular at 0 if and only if all the coefficients of this equation are holomorphic functions at 0. So it's quite a beautiful criterion. You just have to look at the coefficient and then you know if your equation is regular singular at 0 or not. Okay. So, yes, I don't want to say something else here. So now let's talk about some consequences of this property, regular singular point. Okay. First consequence I want to talk about is about their solutions. So solutions of such differential systems, which are regular singular. In fact, the solution of such system have a good analytical property because we have this proposition. I don't know if you can see here. Maybe I can come here. So we have this proposition is that the differential system is regular singular at 0 if and only if all entries of a fundamental matrix of solution. Have moderate growth at 0. Growth at 0. That means that if you're looking on sectors of this form, so you don't take the 0, okay? Like this. Okay. For all alpha, beta, so that is, there exists a radius, okay, such that for all entries, I call them G, you have that there exists an integer and a constancy such that your entries of the fundamental matrix of solution grows lower than this, and we call S alpha beta epsilon this sector. Okay. So, as we can see, the solution of such the entries of solution of such differential systems have good analytical property. For example, in this kind of differential system, you do not have in the solution elements like this, where P is a non-constant polynomial. So you do not have this kind of element which appears in the solution. In fact, this kind of elements are a marker of irregularity of your system. Marker of irregularity. So you do not have this kind of elements here. So as we just see, if you are regular singular at 0, then your solution have good analytical property. So now I will talk about another consequence in the Galois, in the differential Galois theory of this hypothesis. So it's point 2 in differential Galois theory. Differential Galois theory. I will talk about, in particular, density theory. So, if you look at a differential system, we have a group attached to the differential system called the differential Galois group. Galois group. This group is an algebraic group. I will not go into details here. I'll just mention a few points. I will not detail. Okay. And in the case of regular singularities, a theorem of Schlesinger told us that a certain group is Zariski-dense in this differential Galois group. So it's a Schlesinger density theorem. If the differential system is regular singular, I mean that all singularities are regular. Then a certain group called the monodromy group is Zariski-dense in G. I called it G. I will not explain in details what is this group. Just say that this group comes from analytic continuation. Okay? This group comes from analytic continuation. And in the case of regular singular differential system, this group is Zariski-dense in G. If you remove this hypothesis, then you are not this conclusion. Maybe the simplest example, counter example, which is not an example, of this theorem when you remove this hypothesis is the following, okay? So, in fact, here you have a singularity at infinity because if you change the variable, then you have this equation at t equals 0. So if I keep my notation delta, you have this, okay? Yes. And here, the point infinity is a singular point, and it is not regular. You can see it with the Fuchs criterion here. Okay. And I not give details about it, but I just said that it comes from analytic continuation. And here you have the exponential, and if you do analytic continuation with the exponential, it doesn't change. So in fact, here we can compute the monodromy group. It's only the trivial one, okay? And here the Galois group will be the biggest one, which is sister. In fact, the exponential is transcendental function. Okay. So it's not Zariski-dense. So if you remove this hypothesis, you lost the conclusion. In fact, we have a conclusion when the systems are not regular singular. It's due to Jean-Pierre Ramis, who proves that if you add elements called stock matrices and exponential torus, then you have again a Zariski-dense group. But the monodromy group will not be sufficient. Okay. Okay. So we have this density theorem, and we have analogs of this density theorem for other kind of systems, different systems. Okay, is here. So I will just mention two analogs of this density theorem of Schlesinger, which is about these systems. So you have analogs. For example, so we are looking at system of this form where phi is this operator, for example. So you take this instead of the derivation, where Q is this complex number, and we can assume that its modulus is greater than 1. It's called the Q difference systems. Okay. The analog in this case is due to Van der Poot and Singer. It's also due using Picard-Vessiaux theory. Okay. And it's also due to Jacques Solois using Tarnakian categories. It's around okay, and I will mention the case we're interested in this talk. It's the Mahler case. Here for the Mahler, so I called here sigma q, and for the Mahler operator, we called it phi p, which is this one. Okay. So sorry, I have not the same notation as Boris. I called it P instead of Q, and for me Q is this one. Okay, so I keep this notation, and it's a result I've obtained during my PhD. Okay. Okay, I have to mention that in this case, we are not anymore interested in the pole of A. Here, the singularity are not the pole of A as before for differential system. We are looking at the fixed point of phi. Okay? So for example, for Mahler system, we are looking at a point 0, infinity, 1. Okay. So here we are looking at the fixed points. So in the first part, I give you some consequences of this hypothesis of regular singular systems. Now the question is, are we able to recognize when such a system is regular singular? Okay, so it's the second part of my talk. I will talk about algorithm to recognize if a system is regular singular or not. Okay. So second part is recognize regular singular system. So we have a general algorithm to recognize them. General algorithm. This algorithm is due to Barcatou, Bruton, and Flugel. Okay. They give a general algorithm to recognize when systems of this form. So they are looking at system of this form. Okay. Here, phi is an automorphism of a field F. It is a field of characteristic 0. Okay. And D is a phi derivation. So in fact, you have the same rules that for derivations. The only thing we change here with phi derivation is that when you look at the derivation of a product a phi appears, okay? I will not, but just, if you take phi, the identity, then you have a derivation in the usual sense. Okay, so they're looking at such a system. With a general condition, I can write it here. With a general condition on phi and the field F, okay. So they are looking at systems of the form, and for example, their algorithm applies to many classical examples. So for example, it applies to the differential case. So for example, it applies to the differential case. For example, you can take F to be the field of Laurent series. Here, you can take for D the usual derivation, and for phi the identity. Okay. It also applies to a Q difference equation. Okay, so I called it sigma Q. Okay, with the same F. Okay. And here, so it's a phi. And here, D will be the identity of sigma Q. Sorry. So it applies to the difference case. Okay. But in fact, it does not apply to the Mahler case. It's why? Because behind this general condition, the phi must preserve the valuation of the function. So for the Mahler case, you're looking at this operator, and it do not preserve the valuation at 0 on the function. You change the smallest power of z you are in your function. Okay, so it does not preserve, so you can't apply their algorithm to this case. So with Colin Faverjon, we managed to find an algorithm, but it's different from this one. It's different. Okay. So it's my second point, the case of Mahler systems. Mm-hmm. So Mahler systems are nowadays the subject of many studies. And in fact, it's mostly due to their link with automata theory. As Boris Adamczewski told us this morning, you have the link between automata theory and the solution of such system. So here, system in English. So here I will denote like this Mahler system. Okay. So Y is a unknown, and A here will be a matrix with coefficient in the field of rational function. So like took this one. Okay. And by definition, we have the analogous of the definition I've given for differential case is that your Mahler system is regular singular at 0. So I recall I'm interested in the fixed point of the operator, for example 0. If there exists a T, a gauge transformation, whose entries are Puiseux series. So Puiseux series is this field. Okay, such that, and the constant matrix C, sorry. Oh, I don't have the, I need to, such that you have this equality such that, so you have this equality. So here, the unknowns are T and C, and the question is, are we able to construct such T as such C satisfying this equality? If it is the case, your system is regular singular at 0. If it's not the case, it will be not. Okay. So with Colin Faverjon, we prove that this Mahler system is regular singular at 0 if and only if a certain explicit vector space has dimension at least n, where V, I will explain after where this vector space comes from, but let's just mention that it is explicit, okay? Explicit vector space. For the 10 minutes I have, I will give the main idea of the proof of this result. Okay. So this is an explicit result. You can we construct an algorithm implemented in Python, which computes the dimension of such a vector space V and answer if the Mahler system is regular singular at 0 or not. And if it is the case, then the algorithm gives you a matrix C and the series expansion of T as the order you want also. So to explain the ideas of proof, I just restrict to the case where the entries of T are Lorentz series. To explain the main idea. So the main ideas of the proof. Let us look at the case when the Gauss transformation has entries in the field of Lorentz series. Okay. So let us assume that the Mahler system is regular singular at 0, and let's look at the information we can obtain on T and C. They must satisfy certain conditions because they satisfy this equation. So let's look at the condition we can obtain thanks to this equality. The easiest consequence is the fact that if you look at the valuation of T, it is the smallest power of Z appearing in the entries of T. Okay. We have a minoration of this by this integer, an explicit integer called nu, okay? And it's just why, it's just because, sorry, if you look at this, called it star, if you look at this, star is equivalent to this, okay? You take the valuation in this equation. Here you have P times the valuation of T, and the valuation of a product of matrix is greater than the sum of the valuation and the valuation of A plus the valuation of T and the valuation of C, which is 0 because C is constant, okay? And from this, you have this, okay? If don't make mistake. Yes, no, it's okay. I can stay here. So it's the first consequence of if you assume that your system is regular singular at 0. The second consequence, so just mentioned that before, we are happy here because if you look at an expansion of T, you know where you can begin. You can begin with the order nu, okay? So it's like a starting point. So you can write a series expansion of t like this, greater than u. Okay. So now the second information we have is that at a certain point we can obtain this coefficient thanks to a recurrence relation. So you will have a recurrence relation. I will not give details of it, but you have a recurrence relation to determine the Tm when m is greater than a certain integer we call the mu, which is an explicit integer. Okay, this is an implicit integer. So yes, here, as you can see, we managed to obtain a finite problem. We just have, in fact, compute the coefficient of t between nu and mu. Okay? And then the recurrence relation will give you all the t you want. So that's the second information. And because of this second information, we introduce this map, p nu mu, from a vector of Lorentz series to Cn mu plus 1. Okay, I not have the, okay, it's not a good idea to write it here. Okay, I don't have enough place, so I can keep only this one. So this map, P nu mu, which map a vector of Lorentz series to a vector whose coefficients are constant, which is this one, so P nu mu. Okay, vectors. And so you take a vector of Lorentz series, okay, and we just keep the coefficient we are interested in, that is the coefficient between nu and mu, okay, so we put them in a vector like this, okay. So it's the coefficient we want to find to then construct this matrix T. And the last information is this one. If let's call T1, Tn the columns of T, then, and V, I will give you this V. So V is this vector space, K, N, M, K, intersect with K, N, where M and N are block matrices, big block matrices. C, I don't mention the C. No, I don't mention C is this one, is this integer. Okay. And the blocks are the coefficient of the inverse of A. If you write the inverse of A like this, the blocks are the BK. For example, I just give for M because it's not takes place. For M, for example, we have this. Yes, we have this. Okay, so I change. It's Q bar. Okay, I fixed that. Okay. So this vector space V, the idea behind the construction of such vector space is that the map P nu mu sends the columns of T to this vector space V. So I don't explicit the computation, but the idea is that P nu mu, if you look at the image of the columns of T, then it goes to V. It takes into account the relations of the columns of T, because when you have this kind of equation, you may assume that C is a Jordan matrix, because up to conjugation you can assume this. You will have a relation between the columns of T. For example, if C is a diagonal matrix, the columns of T must satisfy certain equation. And you have the same when C is a generally constant matrix. Okay. So, and this vector space here is that to remind you that you have this relation between the columns. Okay, and we proved that this map is injective. Prove that it is injective. So since it's injective, the column of T has dimension n because T is an invertible matrix. So your vector space V must have at least a dimension n here. Okay. So you have the first implication. And the second implication, just mention briefly how it works. This implication is interesting because it's thanks to this implication that we built our algorithm. Okay, so we'll just see how we can construct these matrices. Let's denote M, the dimension of V. Okay, it's at least n. And we put in a matrix called E a basis. It is a basis of V. And then we cut this matrix into matrices called E nu and E mu, etc. Okay, and in fact, these matrices will be the first coefficient of a T. Okay. So you have. So first, we can prove that there exists an invertible M, C, an invertible matrix, sorry, Q bar, okay, C called R such that you have that M times this matrix, M is the one I've given before. So we prove that there exists such matrix. It's because M acts as an isomorphism on E. Okay, so you will have an invertible matrix R. Then we define the A G for G greater than U by a recurrence relation. And the recurrence relations is made such that you have this equality AZ TZ with T, the matrix whose first coefficient are the coefficients here. Okay. So now we are almost done, because as you can imagine, this will be a constant matrix we are looking for, okay? Here, T will be a Gauss transformation, but two things remains to be proved. In fact, here T is not a priori a square matrix, because M is not equal to M a priori. But then we prove that M must be equal to M. So it is a square matrix, and then we prove that T is the invertible. And it's how the algorithm is constructed. The algorithm computes a basis of V. We take these matrices, which will be the first coefficient of a Gauss transformation. The constant matrix returned by the algorithm will be this one, the inverse of this one. Okay? And if you want other coefficient of t, you just use the recurrence relation to find them. Okay. So just here it was the case of coefficient with Laurent series. If you want to deal with coefficient of Puiseux series, you have to have a control on the ramification which appears here. And we managed to obtain this control thanks to the work of Chisak, Dreyfus, Dumas, and Mezzaroba to obtain a control of such ramification. And when you know which ramification can appear, you just apply this case to the system, to this system, where you kill the ramification. So, okay. So, thank you. Yes.
So now you have some gauge transform with coefficient. So now you have some gauge transform with coefficient in the formal power series. Can you improve upon it to get some convergence?
I don't follow the end of the question. So
the
yes.
Transformation is with coefficient in the formal series.
Yes.
Is it possible to obtain a series with better convergence?
With a convergence at 0, for example?
Yes.
Here we're looking at formal series, but I think that you can obtain such... you mean with coefficient? You want to deal with coefficient?
With non-trivial convergence radius.
In this field?
Yes.
Okay.
Or characterize their growth around 0, like you mentioned in the differential case.
Yes. Okay. Yes, in the case of Mahler system, when they are regular singular, you have a kind of analogues of this growth. But it's along, it's not on the same sector. Mm-hmm. It's along singularities. Okay. It's, yes, you have a growth, moderate growth for the solution of such a system when there is a regular singular. It's the analogous of the one I've given for differential system, but we are not looking at the same sectors. We are looking at 0, but not on the sector I've given before. Yeah.
Okay, thank you.
If you have such a Mahler system which is regular singular at 0, does the method give you any sort of Frobenius method to solve it?
Yeah, okay. Yes, we have a Frobenius method for Mahler, in fact for Mahler equation. But to Mahler system, you can transform it thanks to cyclic vector lemma into Mahler equation. And for this, you have a Frobenius method due to Julien Roch. And thanks to this Frobenius method, you can obtain information on the solution. And in fact, with Colin Faverjon, we worked on such kind of equation. So you look at Mahler equation, and thanks to the Frobenius method, we obtain another algorithm to characterize equations which are regular singular at 0, using something completely different from that, but using, as you have said, the Frobenius method. Okay. Okay.
You said that you, in this expansion of the t function, the Tm were explicit, yeah?
Yes.
So what do you mean by that? In what terms? Is it explicit?
You want the recurrence relation? I can give it to you. I have write it. No, it's not so complicated, because if you look at that, then in fact I can write it like this. Okay. Yes. And I can put So if I'm right, you can put it like this, okay? Let's denote by B this matrix. And in fact, if you take, so I call the Tm the coefficient. So you just look at the coefficient of Zm, Z to the power m. And if you look at the coefficient, you have this, if you take the coef of T of Zm, you have this equality. So I call Bk is the coefficient of this matrix, Tl this one, and you have that T plus PL must be equal to M. And in fact, if M is bigger than an explicit integer, which is, I wrote in here? Yes, it's here. If M is greater than this one, you can check that in this sum, the L appearing in this sum are smaller than the M. So you have this, the recurrence relation is just that. Okay.
So it's a rational fraction in terms of the first?
Yes, of the first T, yes. Yes, you need the first coefficient and the coefficient of the inverse of A and the C, okay.
So let's thank Marina again.